to all. I am Dr. SRINIVASAN, Associate Professor, Chemistry Wing of BDE, Annamalai University. Today we are going to see B.SC program, especially Unit 5, second part. First part already we have finished. In Unit 5, second part, Thermochemistry. In Thermochemistry, we are going to see the value of delta H and then sign of delta H, etc., etc. So, what is by thermochemistry? The branch of chemistry that deals with the study of heat changes accompanying a chemical reaction is called thermochemistry. Here we must give importance factor for the delta H value, the sign of delta H. The heat of reaction is expressed in terms of change in enthalpy delta H. In chemical reaction, if heat is evolved, the enthalpy of product is lesser than the enthalpy of reactant. It is very, very important. In such a cases, the change in the enthalpy is represented by negative sign. It means that negative delta H. In chemical reaction, if heat is absorbed, the enthalpy of product is greater than the enthalpy of reactant. In such cases, the change in the enthalpy is represented by positive sign. It means that plus delta H. Enthalpy of formation. Enthalpy of formation may be defined as the change in the enthalpy which occurs during the formation of 1 mole of the substance from its elements in their standard state. Enthalpy of formation may be positive or negative depending upon the nature of the substance formed. For example, formation of ethane, formation of methane. So, carbon reacting with the hydrogen gives rise to C2H4. The delta H value is negative 890.3 kilojoule. Similarly, formation of methane, carbon with the hydrogen gives rise to CH4. The delta H value is negative 75.3 kilojoule. Enthalpy of neutralization. Enthalpy of neutralization may be defined as the change in the enthalpy when 1 gram equivalent of an acid is neutralized by 1 gram equivalent of base in dilute solution. Consider the following reactions involving strong acids and strong base. HNO3, one kind of strong acid, NaOH, one kind of strong base. So, in this reaction your product is sodium nitrate with water. Corresponding delta H value is minus 57.28 kilojoule. Similarly, we may consider potassium hydroxide with nitric acid. So, nitric acid is reacting with the potassium hydroxide, gives rise to potassium nitrate as a neutral salt with H2O. Here the delta H value is minus 57.85 kilojoule. Similarly, we may consider hydrochloric acid, one kind of strong acid is reacting with a strong base like sodium hydroxide, gives rise to sodium chloride as a neutral salt with water. The obtained delta H value is minus 57.32 kilojoule. So, last one, hydrochloric acid, one kind of strong acid is reacting with potassium hydroxide, strong base, gives rise to potassium chloride as a neutral salt with H2O. The obtained delta H value is minus 57.45 kilojoules. An almost constant value is observed in all 4 reactions, and hence approximately minus 57.4 kilojoule can be taken as the enthalpy of neutralization when both the acid and the base are strong. If you are considering all 4 values, so first one is delta H is minus 57.28, second one is 57.85, third one is 57.32, the last one is minus 57.45. In all the categories we are having 57 as a constant value for strong acid and strong base. Similarly, in other neutralization reactions also the net reaction is the same, hence the constant value is obtained in all the cases. This constancy will not be noticed if acid or base is weak or both are weak. Consider the following reactions. For example, we may consider hydrochloric acid is a strong acid. The well known weak base ammonium hydroxide gives rise to ammonium chloride as a neutral salt with water. So, in this case that obtained delta H value is minus 51.48 kilojoule. Second one, acetic acid, one kind of weak acid with a strong base like sodium hydroxide. So, acetic acid is reacting with the sodium hydroxide, gives rise to sodium acetate as a product with the water. Here obtained delta H value is minus 55.23 kilojoules. And third one, acetic acid is one kind of weak acid. Similarly, we may consider weak base ammonium hydroxide. So, acetic acid is reacting with the ammonium hydroxide, both are weak system. So, this reaction, our product is ammonium acetate with the water, that obtained delta H value is minus 49.8 kilojoule. In all the above cases, the enthalpy of neutralization is less than 57.4. Already we have seen in the case of strong acid with a strong base, we are getting minus 57 as a constant value, but in this case less than 57, because weak acid and weak base will be only partly ionized in solution. So, they have to completely ionized during the neutralization reaction. So, for the purpose of complete ionization, certain amount of heat is used, hence it may be lesser than that observed value. Next, laws of thermochemistry. Here we are going to see major laws, two laws, Lavoisier and Laplace law, Hess law. In the heat exchange in chemical reactions are governed by these two major laws in thermochemistry. First one, Lavoisier and Laplace law. This law states that the quantity of heat evolved, sometimes observed in the course of chemical reaction, is exactly equal to quantity of heat observed or evolved when the reaction is reversed. The law states that the quantity of heat evolved or observed in the course of chemical reaction is exactly equal to the quantity of heat observed or evolved when the reaction is reversed. This means that the heat of formation of compound is numerically equal to its heat of decomposition, but with opposite sign. So, hydrogen is reacting with half of the mole of oxygen, gives rise to water. Another one process, H2O may be decomposed, H2 plus half of the mole of oxygen. In both the case, that first one is having the delta H value minus 285.8 kilojoule, second one is plus 285.8 kilojoule. Hess law of constant heat summation. This law states that the enthalpy changes of the given chemical reaction is the same whether the process takes place in one steps or several steps, single step or several steps. Example, carbon is converted into carbon dioxide directly by heating with the excess of oxygen, and the change in the enthalpy is minus 393.7 kilojoule. So, the formation of carbon dioxide we may consider in three steps. So, first one, direct process, carbon may react with the oxygen, gives rise to carbon dioxide. In this case, that obtained delta H value is minus 393.7 kilojoule. Alternatively, carbon is first converted into carbon monoxide by heating with a limited amount of oxygen. This carbon monoxide is then converted into carbon dioxide. So, that second process we may consider two-step process. So, first one is a single process. In this case, we are getting minus 393.7 kilojoule only. The second steps we are going to consider that the product carbon dioxide by two different steps. So, first one is carbon is reacting with half of the mole of oxygen, gives rise to carbon monoxide. The delta H value is minus 110.5 kilojoule. That second process is carbon monoxide is reacting with half of the mole of oxygen, gives rise to carbon dioxide. The delta H2 value is minus 283.23 kilojoule. If you are considering these two processes, the total delta H value is minus 393.7 kilojoule. So, initially we have seen that formation of carbon dioxide in single step, the delta H value is minus 393.7 kilojoule. Similarly, if the reactions are taking place in several steps, in the case of formation of carbon dioxide, that final delta H value is minus 393.7 kilojoule. So, the reaction, whether this reaction are taking place single step or several steps, the total enthalpy value will be the same. So, now we have proved based on these three equations. The total enthalpy change in both the steps is found to be minus 393.7 kilojoule, since the change in the enthalpy in one step or two steps is found to be identical. It proves Hess law. With the help of this law, enthalpy changes can be calculated for reaction which direct experimental measurement are difficult. For example, it is rather difficult to measure the enthalpy change for the partial combustion of carbon to carbon monoxide. So, now we are considering in the form of carbon as a graphite form. So, carbon with half of the mole of oxygen gives rise to carbon monoxide. Here we are going to calculate the delta H value. However, the enthalpy of formation of 1 mole of carbon dioxide is known from the reaction. So, carbon is reacting with the oxygen, gives rise to carbon dioxide. Here the delta H1 value is minus 393.5 kilojoule. The formation of carbon dioxide can also takes place as follows. So, here we may consider two steps. Carbon with half of the mole of oxygen gives rise to carbon monoxide. Here delta H2 value is we are going to calculate. So, carbon monoxide is reacting with half of the mole of oxygen gives rise to carbon dioxide. Here that obtained delta H value is minus 282 kilojoule. So, basically if we may consider delta H2 and delta H3. So, addition of delta H2 with H3, we are getting minus 393.5 kilojoule. So, we may calculate that delta H2 value. So, delta H2 minus 283 is equal to minus 393.5 kilojoule. So, automatically we may calculate the delta H2 value minus 111.5 kilojoule. Next, Kirchhoff's equation. Kirchhoff's equation gives the relationship between variation in heat of reaction with the temperature. It can be stated as the change in the heat of reaction at constant pressure for every degree change of temperature is equal to change in heat capacity at constant pressure accompanying the reaction. So, consider the general reaction. A gives B as shown in picture. For example, the process A is reaching to B. Similarly, in second process A is reaching to B, only the delta H and delta H2, H1, H2 value is different. Similarly, the temperature also different. So, first one is having T1 temperature, second one is having T2 temperature. So, based on the figure we may consider that is first one is path 1, second one is path 2. So, both are having different delta H value. Similarly, both are having different temperature values. Now, starting from A at temperature T1, we can reach B at temperature T2 by two different paths. In path 1, we may allow the reaction to take place at temperature T1 to obtain B at the same temperature and the heat this up to the temperature T2. Then heat evolved in first stage is equal to delta H1. Heat absorbed in the second stage is equal to CPP T2 minus T1, where CPB is average molar heat capacity of the product. Net heat evolved delta H1 minus CP T2 minus T1. Here CPB is average molar heat capacity of product. Path 2, when first heat up the reactant to the temperature T2 and then allow them to react to give the product at the same temperature, then if CPA is the average molar heat capacity of the reactant A, because here we are considering that reactant A gives rise to B as a product. So, heat absorbed in the first stage CPA T2 minus T1. Heat evolved in second stage is equal to delta H2. The net heat evolved may be calculated delta H2 minus CPA T2 minus T1. Now, since the initial and final states are the same in both the above cases, therefore, by law of conservation of energy, we must have net heat evolved by path 1 is equal to net heat evolved by path 2. So, delta H1 minus Cp T2 minus T1 is equal to, in the case of second path, delta H2 minus Cpa T2 minus T1. So, automatically from this equation we may calculate that heat capacity of Cp, I mean delta Cp. So, delta H2 minus delta H1 divided by T2 minus T1. So, this kind of equation obtained from initial equation, I mean while rearranging that initial equation, automatically we may get that Cp values. When the reaction is carried out at a constant volume, we have the thermodynamic reaction, that is delta H is equal to delta E plus P delta V. This is well known equation in thermodynamics. Under conditions of constant volume, if we are putting delta V is equal to 0 means automatically that equation becomes delta H is equal to delta E. Hence, that equation derived above takes the form E2 minus delta E1 divided by T2 minus T1 is equal to delta Cv. Delta E2 minus delta E1 by T2 minus T1 is equal to delta Cv, where delta Cv is equal to heat capacity at constant volume for product B minus heat capacity at constant volume of product A is change in the heat capacity at constant volume. So, Cpv, Cvb and Cva are the mean molar heat capacities at constant volume of the reactant and the product respectively. So, delta E1 and delta E2 are the internal energy changes, that is heat of reaction at constant volume when the reaction is carried out at constant temperature T1 and T2 respectively. The Kirchhoff equation may also be expressed as the change in the heat of reaction at constant volume for every degree change of temperature is equal to change in the heat capacity at constant volume accompanying the reactions. Summary: the thermochemistry deals with the study of heat changes accompanying a chemical reaction. The heat for formation, neutralization, Hess law of constant heat summation and Kirchhoff's equations are learned and understood. So, for this purpose we may consider reference books Physical Chemistry Samuel Gladstone, similarly Basic Principle Physical Chemistry Puri Sharma and Padania. So, such type of books may be recommended to refer such type of topics in detailed manner. So, thank you so much.